Well, this leaves us, the interesting question is, how do you draw a direction field? Well, this being 2003, mostly computers draw them for you. Nonetheless, you do have to know a certain amount. I've given you a couple of exercises where you have to draw the direction field yourself. This is so you get a feeling for it, and also because humans don't draw direction fields the same way computers do. So let's first of all, how do computers do it? They are very stupid. There's no problem. Since they go very fast and have unlimited amounts of energy to waste, the computer method is the naive one. You pick the point, a point, and they're usually equally spaced. You determine some spacing. This point, that one, blah, 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 blah. Equally spaced. And at each point, it computes f of x, y at the point. Finds means it computes the value of f of x, y, that function. And the next thing is, on the screen, it draws at x, y, the little line element, having slope f of x, y. In other words, it does what the differential equation tells it to do, and the only thing that it does is if you're telling the thing to draw the direction field, about the only option you have is telling what the spacing should be. And sometimes people don't like to see a whole line. They only like to see a little bit of a half line. And you can sometimes tell, according to the program, tell the computer how long you want that line to be, if you want it teeny or a little bigger. And once in a while you want an arrow on it, but not right now. OK, that's what a computer does. Now, what does a human do? This is what it means to be human. You use your intelligence. From the human point of view, this stuff has been done in the wrong order. And the reason it has been done in the wrong order, because for each new point, it requires the recalculation of f of x and y. That is horrible. The computer doesn't mind, but a human does. So for human, the way to do it is not to begin by picking the point, but to begin by picking the slope that you would like to see. So you begin by pick the slope. Let's call it the value of the slope c. So you pick a number. C is 2. I want to see where are all the points in the plane where the slope of that line element would be 2. Well, they will satisfy an equation. The equation is f of x, y equals, in general, it will be c. So what you do is plot this. Plot the equation. Plot this equation. Notice it's not the differential equation. You can't exactly plot a differential equation. It's a curve, an ordinary curve. But which curve will depend. It's in fact, from the 1802 point of view, it's the level curve of c. But we're not, the level curve of, it's a level curve of f of x, y, the function f of x and y, corresponding to the level value c. But we're not going to call it that because this is not 1802. Instead, we're going to call it an isocline. And then you plot, well, you've done it. So you've got this isocline, except I'm going to use solution curve, solid lines only for integral curves. When we do plot isoclines to indicate that they're not solutions, we'll use dashed lines for doing them. One of the computer things does, and the other one doesn't, but it won't. They use different colors also. There are different ways of telling you what's an isocline and what's a solution curve. So, and what do you do? So these are all the points where the slope is going to be c, and now what you do is draw in as many as you want of line elements having slope c. Notice how efficient that is. If you want 50 million of them and have the time, draw in 50 million. If 2 or 3 are enough, draw in 2 or 3. You'll be looking at the picture. You'll see what the curve looks like, and that will that will give you your judgment as to how you're to do that. So in general, a picture drawn that way, you'll have so let's say an isocline corresponding to C equals 0, and the line elements along it. I think for an isocline, for the purposes of this lecture, it would be a good idea to put isoclines. Okay, so I'm going to put solution curves in pink, or whatever this color is, and isoclines are going to be in orange, I guess. So isocline represented by a dashed line, and now you'll put in the line elements. We'll need lots of chalk for that, so I'll use white chalk. Why horizontal? Well, because according to this, the slope is supposed to be 0 there. And in the same way, how about an isocline where the slope is -1? Let's suppose here C is equal to -1. Okay, then it will look like this. These are supposed to be lines of slope -1. Don't shoot me if they're not. So that's the principle. So this is how you'll fill up the plane to draw a direction field, by plotting the isoclines first. And then once you have the isoclines there, you'll have line elements and you can draw a direction field. Okay, so for the next few minutes, I'd like to work a couple of examples for you to show how this works out in practice. So the first equation is going to be y prime equals minus x over y. Okay. First thing, what are the isoclines? Well, the isoclines, I've got to carry these with me. The isoclines are going to be y, well, negative x over y is equal to c. Maybe I better make 2 steps out of this. Minus x over y is equal to c. But of course, nobody draws a curve in that form. You'll want it as in the form y equals minus 1 over c times x. So there's our isocline. Why don't I put that up in orange since it's going to be, that's the way, the color I'll draw it in also. In other words, for different values of c, now this thing is a line. It's a line, in fact, through the origin. This looks pretty simple, okay? So here's our plane. The isoclines are going to be lines through the origin. And now let's put them in. Suppose, for example, c is equal to 1. Well, if c is equal to 1, then it's the line y equals minus x. So this is the isocline. I'll put down here c equals minus 1. And along it, something's wrong. I'm sorry? C is equal to 1, not negative 1, right. Thanks. So c equals 1, so it should be little line segments of slope 1 will be the line elements, things of slope 1. Okay, now how about c equals negative 1? If c equals negative 1, then it's the line y equals x. And so that's the isocline. Notice still dashed because these are isoclines and not. Here c is negative 1, and so the slope elements look like this. Notice they're perpendicular. Now, notice that they're always going to be perpendicular because to the line, because the slope of this line is minus 1 over c, but the slope of the line element is going to be c. Those numbers, minus 1 over c and c, are negative reciprocals, and you know the two lines whose slopes are negative reciprocals are perpendicular. So the line elements are always going to be perpendicular to these, and therefore I hardly even have to bother doing any more calculation. Here's going to be, well, how about this one? Here's a controversial isocline. Is that an isocline? Well, wait a minute. That doesn't correspond to anything looking like this. Aha, but it would if I put C multiplied through by C. And then it would correspond to C being 0. In other words, don't write it like this. Multiply through by C, it will read cy equals negative x. And then when C is 0, I'll have x equals 0, which is exactly the y-axis. So that really is included. How about the x-axis? Well, the x-axis is not included. However, most people include it anyway. This is very common to be sort of sloppy and bending the edges of corners a little bit, you know, and hoping nobody will notice. We'll say that corresponds to C equals infinity. I hope nobody wants to fight about that. If you do, go fight with somebody else. So if C is infinity, that means the line, little line segment should have infinite slope, and by common consent, that means it should be vertical. And so we can even count this as sort of an isocline, and if, you know, I'll make the dashes smaller to indicate it has a lower status than the others. And I'll put this in, do this weaselly thing of putting it in quotation marks to indicate that I'm not responsible for it.